right. I'm excited to be back for another session of Powering the AI Stack. Today we have an amazing guest with us, Sean James. Also we always have an amazing co-host, Barak Turovsky with us. So a good way for us to sort of get started here is to do a little level set and chat, sort of about some of the news events driving or at least top of mind, showing why this discussion is really timely. So, one of the things Barak and I have been talking about is just kind of the temporary power generations and really digging into that and what's going on with X.AI in Nashville. Barak, you want to talk about that a little bit?
Yes, again, I think you're way more into details, but I think seeing what's going on and how, to some extent, Elon Musk and XAI are trying to defy traditional wisdom of it takes long time. It's very, refreshing. Obviously, he's violating every possible environmental law, and I'm not sure it's sustainable even for him. But I think to me, it actually reiterates a meta point that there is a mismatch in timeline between demand and supply, right? And what's important is to realize that you will be making decisions when you plan for it based on the complete information. But more importantly, you need to understand every part of the stack. And there are things you can try to optimize, maybe not extreme way as Elon Musk is doing, but you can do some of those stuff. And that's why it's so important to understand it, because you can actually do something about it.
Yeah, no, absolutely. And I guess the other piece that, kind of caught my eye is GTC and sort of all the events around what the next generation of AI factory and density looks like. And folks are talking about, within really like a year and a half or two, density is getting up to like 600 kW a rack, which we were sort of talking in, when we started this session, like, in some distant future, there's going to be a quarter of a megawatt a rack. And it's like that distant future is not so far away. And so that's kind of a crazy deal. One of the things we always like to do is talk about the 4 C's and kind of the framework that we've laid out to keep some of these things organized. And so just as a refresher and a reminder, really consumption and demand drives all of this stuff, right? If nobody wants to use AI, then we don't have to build a lot of things and it doesn't have to be grid scale. And so we're always kind of keeping an eye on, what are leading indicators of consumption? How are people using it? What's the enterprise doing? It's always going to be kind of an important thing. Then cognition. And so thinking about the data, the various models, whether it's DeepSeek or some of the new frontier models, that's always sort of how efficient and how performant and what do they need. Compute, so really thinking about the accelerators, GPUs or TPUs or other things, rack level things in the data center, and then ultimately capacity, right? So how much power, does it need water, building level, how does it integrate into the sort of other parts of the industrial and normal built environment? And so that's kind of the 4 C's. And then, one of the things Barak really digs into and that I love is the difference in timeline. So I'll hand it over to him for that.
Yes, and basically the key is I think that's where we're having this mantra is to understand the timeline mismatch. And I learned it hard way when I was at Google building first LLMs, looking at those timelines. But on a basic level, you have the consumption or demand that's extremely fluid. It was always fluid, but it's even more fluid now when we have this AI revolution and democratized access to AI models that everybody could try and demand could go up and down, etc. Then you go to cognition, to models. And obviously now with, democratization of access and being able to fine tune models, it's actually relatively fluid. Yes, might take months, maybe a year to develop a new model, but it's still relatively fluid. And then you're going to harder things. When you're going to compute infrastructure, data center infrastructure, racks and GPUs, etc. You're talking about and putting GPUs into this infrastructure. You're talking about years. You're talking about 12 to 48 months. And then the kicker is, even I was not as aware of it, and that's why I love to partner with Ilya on this, is that on the capacity side, on cooling and power capacity, you're talking about minimum 4+ years. In some cases, you need to make a decision that will basically impact decades of planning, right? And that's why we came up with this idea of this podcast. And what I like to partner with Ilya, we both have deep experience in AI, but from different starting point. I'm more from the consumption and cognition, and understand some of the data center stuff, because we basically, as we productized first LLM with Google Translate, we worked on it. And Ilya coming from capacity and compute, and we both feel that we can contribute to each other to the discussion. But more importantly, we're bringing amazing speakers to contribute to those discussions in every part of the stack, from investors to AI practitioners to model developers to data center planners and to power generation experts. So in the previous sessions, we brought people that understand the data center side or AI model side. And now we are very excited to host Sean James, who basically working as a pioneer and leader at Microsoft in data center architecture and energy systems. So welcome, Sean.
Thanks a lot. It's great to be here. I'm looking forward to chatting with you.
Yeah, and it'd be great, Sean, if you could spend maybe a minute or two just giving us your background. I could definitely take a shot, but I think you do a much more interesting job of kind of introducing yourself and helping us set the table for the discussion here.
Yeah, I appreciate that. I've been in the data center industry since 2000. When I left high school, I enlisted in the Navy and joined the submarine fleet. The goal was to get the GI Bill and get out, and I did that, and I was able to use the GI Bill and get a degree in IT. But when I struck out to get a job, my first job was at this strange building called the data center, and I'd never heard of this thing before. But one of the things that was interesting is that it kind of had the same discipline and a lot of the same systems that a submarine has, right? So everything needs to be redundant, right? You got to keep the load up at all times. Data centers even have a GPS antenna, which is interesting, but for time, obviously. And so I've held a number of roles inside of data centers, from operations to in operations, both the IT side and the mechanical electrical side, to construction, to design, energy. Here recently, my focus has been on introducing new designs and new technology into the data center.
That's awesome. Yeah. And so we've kind of titled this talk "The Good, the Bad, and the Ugly of AI Data Center Energy."
And I think
say again?
Reminds me of Clint Eastwood movie.
That's right. Or there's some good. Next, it's going to be the Dirty Dozen of data centers, right?
Ooh,
but I think in order to really have that discussion, it's probably a good place to just start with, the current state of the grid and why this is even sort of topical, right? Why should we be deeply thinking about this question? And so maybe it'd be good to start with kind of a question to you from your perspective as somebody kind of thinking about deploying data centers, and as data centers are scaling up, what's kind of the current state of power infrastructure as it pertains to data centers, and maybe some of the primary considerations? Yeah,
in short, it's hurry up and wait, unless you get lucky and find a great site. A little bit of the history is, I think, 20 plus years ago, when first of all, data centers were new, we weren't a huge part of the grid planning agenda. But when you needed capacity, it was kind of a transaction, right? You work with the utility, you get a timeline in place, the utility does the upgrades, brings the feeders to your data center, right? It was pretty straightforward. I think as demand for data centers has accelerated over the years, that's where data centers have sort of outpaced grids. So just an observation, there's a lot of asynchrony between a data center's planning horizon and a utility's utilities can't plan underneath 10 years very well. We can't plan outside of 5 years very well, 3 years, if to be fair. And so that creates some novel challenges, but also creates some really good opportunities.
Yeah, no, that makes sense. And I think that, sort of that traditional grid solutions and, just highlighting that normal 10-year power cycle, in the prep for this, we were kind of talking about not just the amount of power, but sort of how some of that power ramps up, ramps down. In another conversation this week, I was actually chatting with another colleague about how some of the larger clusters are starting to think about workloads for GPUs that aren't actually used for training or inference, just to make sure that the data center doesn't spike, right? And so there's some interesting sort of things that to think about that a traditional, hyperscaler data center doesn't necessarily behave how a kind of an AI factory or something like that does. And so, kind of challenging for planners as well. One of the things to that point that these things are bigger and are becoming kind of enough of a consideration that's come out recently is things like the Duke study and talking about how data centers can interact with the grid in a different way. And so, there's definitely challenges that it's harder to deliver that much power for things that are kind of new and not as well understood maybe. But it seems like there's some opportunities that are being kind of highlighted as well.
You're absolutely right. I think that so first of all, the scale drives us to innovate. Anything that you do when you then transition to doing that at scale, like just everything changes. At one time, we talked in terms of data center planning. We talked in terms of maybe like hundreds of kilowatts, and then over time we're talking about hundreds of megawatts. Now we throw around the gigawatt term like it's nothing, and who knows? Maybe someday we'll be talking about terawatts. We'll have to just put a Dyson sphere around a star or something like that. What new opportunities popped up? Probably for me, it was about 5 years ago, maybe longer, when we had this opportunity in Cheyenne to really reduce the cost of the energy of the data center and accelerate the time to get capacity, right? To do it more efficiently, to eliminate the need of a power plant. So like all of the good stuff that we like to see in the data center industry. And that was, like I said, in Cheyenne, Wyoming. And you can read about this online. In Cheyenne, Wyoming, when the utility said, hey, your forecast growth is larger, than this entire market right here. We're gonna have to build a power plant, and we had just hired some just outstanding energy experts that were kind of just looking at the logic. And they're like, well, hey, wait a minute, we're gonna build a power plant on site with standby generation. Let's just build one, right? And then we were able to work together. And this is the key thing in order to make this stuff work, is being at the table and figuring out each other's language and figuring this stuff out together. And we were able to come up with a really good project where the data center is one of the grid's assets. And throughout the year, when the grid needs capacity, the data center is on that list. This was a really good kind of first case for data center flexibility. And now I see it popping up all over. The second case was us being able to utilize UPSs for grid services as well. And so in one case, it was in the Cheyenne case, it was all about capacity. In the case with UPSs, it was about other grid services that are very, very important to keep the grid stable, which is good for everybody. So yeah, I was really excited, to see not only the Duke paper, but EPRI has now a data center flex. This last report that came out last week or a week before from the International Energy Agency, this is a global think tank, dedicated a lot to this new ability for data centers to be flexible and all of this goodness that comes out of it. So I'm super excited about it.
Yeah, it does. It's crazy that it seems like it is sort of report season, because in the last month, I've been reading like almost unexpected amount of reporting on a lot of these topics. Historically, when Barak and I have been discussing this, Barak points out, and by the way, just to point out that rate tariff from Cheyenne, I think was like 2016, right? I just shared an article about it. So that's almost a decade ago, right? Yeah. So that's on the very, very leading edge of, some of these.
That's when we released our first LLM. So it's kind of, probably coincidence, but it's very relevant.
Yeah. And it's crazy because it's amazing when you do, especially like in infrastructure and more traditional things, once somebody figures it out, all of a sudden, a few years later, everybody's on the phone trying to figure out, hey, how'd you guys do that? Whether it's from the business side or operational side, or even like how do you have that conversation in a way that is constructive? So kudos to you.
It does start with, you guys are crazy. And then people understand it. And then it's, hey, how'd you do that? Right. And I love that arc. It's so much fun.
Yeah. Well, and one of the things, maybe I wanted to toss it back to Rock for a second, in our conversations about, you're feeling like you're having flashbacks to the past. One of the things Barak points out is, historically, you're always going to overcommit or undercommit. You just don't know which way it's going to go. So maybe Barak spending a minute or two just kind of highlighting that and talking through it a little bit.
Yeah, so that's is coming from the experience. Well, there's multiple experience. Data center and power do not come with AI. It's just AI just increase. We had everybody knows the story about Amazon of how AWS was born, because they're basically overbuilt and overcommitted on demands that crashed after first .com boom and bust. And basically they said, okay, we have excess capacity, so they started to find a way to use it. So that's one story. The second story is that Google in early 2000 basically was growing like crazy, and they were very deliberate on basically making sure they have capacity. So they basically, the approach was build, and they hired people that have those fancy titles of head of special projects that were basically going to counties, buying land with, access to water and grid. And that went really well for many, many years. But then 2008, a recession happened, and Google is like, okay, let's tighten the screws. So they tightened the screws, and then boom, 2012, everything is booming again, and Google has capacity problems. So they had to go to extra measures. I was already at Google. There were people that were assigned, specifically Urs Hosles, who was like SVP, like employee number 9, and was SVP of technical infrastructure. So he became a capacity czar. He would personally review all projects with big compute. That's before GPU, that was CPUs at that time, right? With big compute commit, he would review it and basically making sure that, it's not spent on the right things. And I think AI happened. We had the same thing, in 2016, we were productizing first what we now call LLM with Google Translate. We discovered all those issues with inference that now people are rediscovering it, that, you could train for, couple of weeks, but it's not a big deal, at least in translation. That was Google Translate was the first product. It was not a big deal because, languages do not change that much, but inference was 100x slower. So we effectively had, and GPUs at that time sucked. So we basically had to go and had very honest discussion with Jensen and NVIDIA and said, hey, sorry, it's not working. We will need to develop our own. And to their credit, they took it really, they took it to heart. And now GPUs are really capable on both on training and inference. That said, there are interesting startups that are doing stuff on the chipset, either for inference or training. And I hope we will actually bring some of those startups to talk here. So yeah, there was a lot of lessons learned, but the key is back to the point is like, you cannot predict when you have a very flexible demand. You cannot predict how demand will behave. You cannot predict what models will behave because models are way more fluid to develop. And one day it's like, oh, the model is very big. And the next day DeepSeek comes and saying, well, the model doesn't have to be big, or to develop a relatively big model, it's relatively cheap. So you need to basically to know that you'll make decisions based on complete information, and be very thoughtful and bring experts and understand each part of the stack. That's what we're focusing in this podcast.
It's actually kind of interesting. Kind of is a good transition. Sean, you already started to talk about a little bit of the kind of behind the meter powertrain at the data center. The traditional footprint has been some kind of backup generator, some kind of UPS, so, power supply that can't be interrupted. And all of that was really focused toward making sure that your CPUs or GPUs or whatever the computing element was never turned off. But it's interesting to think about sort of the arc that Barak was just describing with, sort of innovation and reconfiguration of that powertrain for different applications. So maybe we could start with that a little bit is, whether it's capacity, sort of uptime or things like that, what are some of the things that you're thinking about when you're thinking about kind of the next generation powertrain? And then that could be sort of a good way to set the table for all the cool and goofy and innovative things going on that we can talk about for a little while.
Hey, one really good innovation that's come about in the last few years is just data centers realizing that not every data center needs standby generators. Most of them do, though. Okay, so I don't want to say the future is, no generators, but there are some applications, that don't. And so you see that, right? And you see that in the news that, okay, this data center over here, the type of application that was on it, it doesn't need that high availability, right? The term we use in the industry is 5 nines, right? The power, the application, right? The server has to be up for 99.999% of the year. And in order to achieve that, and it's all calculated, in order to achieve that, you got to look upstream, because none of that equipment upstream has that high of availability. It's the system, right? The integrated system of the redundant buses, of the standby generators, of the UPSs, of the grid, sometimes, two or more grids coming into a site. So that's really important. So that's the first innovation. The second innovation that is much more recent is what can we use instead of diesel generators, these NFPA, diesel gens that have been just used forever. And the dirty secret is they're not as reliable as a lot of people think. I think when you're in operations, you're kind of holding your breath when it's time to start those generators. Is it really going to start or not? And so this sort of this sentiment to try to look for something better. Whether it's tier 4 generators or natural gas generators or hydrogen fuel cells or potentially batteries, right? This is where we're at right now. How do we do this better? How do we have this standby generation that's better?
Yeah, the thing that actually gets me is everybody, especially from around the four Cs, is always really aware of the deep, technical, complicated, convoluted things from their category, and thinks everybody else is like got no problems, right? Because my problems for designing the next algorithm are crazy. I'm competing with the world, whatever, but it's, you started talking about gas generation, for example. Even in gas generation, thinking about the difference between like a reciprocal engine versus a larger turbine, and what is the cost ultimately of power, but then more importantly, how quickly can you spin this thing up and down, and what role does it play, is actually like a non-trivial question, right? And then there's also, obviously, I won't get into supply chain shortages and all that other stuff, right? But even just how fast do you need power? What do you need power for? And then how do you sort of get it both for the data center itself versus, are we doing something for the grid as well, right? And it's just like, it's crazy to think about sort of the degrees of freedom in the complexity of some of these problems.
Yeah, I think a lot of people who haven't gone through an on-site generation project probably have less sympathy for the complexity that's involved with picking the right generator, and how does that impact the rest of the integrated system in the data center. For example, if you just pick any old turbine out of the catalog, that might require 10 or more minutes to start up. And when you throw big block loads on it, it could slow down. So that's the first issue. The second issue are things like footprint, emissions, the pressure of gas coming into the site, right? So there's a lot of complexity. What about running a gas piping network throughout the campus, right? This is a brand new area.
Yeah, actually, one of the questions that's come in is talking about, natural gas, at least in the short term, is playing a much bigger role. And, gas companies don't operate quite like the traditional utilities do. And so, are there sort of considerations, or how should folks think about that? It's interesting. It's been interesting to me looking at sort of natural gas capacity become more and more of a siting criteria. First, the Bill, who's asking the question here, was saying people chase fiber, then they chase kilowatts. In some cases, they're now chasing on-power access to, or on-site access to gas. And so it's interesting how to see that evolve as well. But any kind of thoughts or experience on, interfacing with gas and then running that through the campus that is worth sharing here?
Yeah, I've got a lot of really interesting stories. Like I said earlier, it's not trivial. You don't just get a pipe. You don't just ask the utility to send a pipeline to your property line. You do need to do some due diligence. A lot of time, the reputation the gas network has is it's very reliable, very redundant. Well, it is in a lot of places, but not everywhere. So you do need to spend some time doing some due diligence. how far up the stream is the nearest storage station, where are the compressors at, are the compressors powered from the grid? So if there's a grid outage, you're going to lose gas anyway, right? So that's not insignificant. The quality of the gas, gas isn't just methane. There's other molecules that are in there, and that can affect, things like the heat rate and how the generator performs. So that's a big deal. What about redundancy? I mean, if this is your sole source of power, these gas lines, these gas lines do need to go down for maintenance. You have to, a lot of these gas pipes are steel, so you have to check them for corrosion, things of that nature. So redundancy is a big deal. And then what about your distribution inside your site? That needs to be very robust as well. I think there's an assumption that, hey, as long as you can locate next to gas, that you're going to be just as good as, if you found a very large feeder. And I'm here to tell you that that's really not the case. It actually adds, it's not impossible, but it adds another level of complexity. For example, one of the benefits of connecting to the grid is just the inertia. So when you need to just instantly ramp your data center, the broader, and I'm typically talking about the US grid here, but it's very stiff, right? When you are just connected directly to a generator, not every on-site generator can handle these big block loads. Well, that's essential for your on-site generation. The other thing is just having on-site generation, I don't think it gives you any sort of unique benefits. So I really think prime power is going to be the exception. It obviously works really well for bridging. Hey, the grids can't deliver you your feeders in the timeline you need it, so you put in some temporary generation. I think that's an outstanding application. But I think it's going to be the exception versus the rule.
Yeah, that's a good point, Sean. And I'm just curious using analogy on a model side, one of the things that I constantly tell people, AI practitioners, that because of the, all this overhype on AI, basically what ChatGPT did is democratize access, but this access is to try and to play with things. And obviously it's easy to raise money and create a really nice, cool demo, but when you're going to productize and when the rubber hits the road, it's actually pretty complex. Not because of AI, it's just the nature of, Pareto principle, that you spend a lot of effort on, on 20% or 10% of the road for real productization. Do you think it's an analogy here that for example, what XAI did, it's very good to grab a lot of attention and basically get it up and running quickly. But if you want to run it for a long time at scale, it might be more of a temporary solution.
Yeah, what I know of that project is it was very successful in making use of temporary infrastructure to get online fast. And you can do things with training data, with AI training data centers that you would never do with other types of data centers. And temporary infrastructure is one of those, right? It's a great way to take advantage of that, these sort of bridging solutions.
Yeah, it's a great point. And XAI, obviously, as our biggest focus right now is bigger and bigger and better models. And maybe you can actually afford temporarily downtime because, it's the end of the day, it's your timelines, right? But obviously, if you need to do it for inference, that's just not going to work. It's a very good point. Thank you for clarifying that.
One thing to point out, by the way, and maybe just to plus one Sean's comments, is when you think about running a power generation fleet, on the grid itself, the expected uptime of a traditional generating asset is 90%, right? So you have scheduled maintenance. You can go in there and do all the things Sean was talking about on the data center side, except on the genset itself. If you were actually relying on your on-site generation to deliver with the same reliability that the grid would need to deliver, you have to design a completely different system, right? And there's just not a lot of those systems that exist, right? There are some applications that run their gensets that way, but it's just not the majority. And so when folks say yeah, I'll just put a gas plant behind the meter, right? Now they're talking about maybe 4 nines, right? And that's just gas plants aren't designed with 4 nines of uptime for the vast, vast, vast majority of all the gas plants that are built in the world, right? And so just questions like that, I just wanted to kind of highlight. The other thing actually that's useful from kind of climate tech and deep tech is a lot of the time the balance of plant, sort of all the things that are necessary to connect your widget with the rest of the system actually represents 50% or more of the cost, right? So as you get really, really clever about, hey, I'm going to have, this type of thing for capacity and this kind of thing for energy and this other thing, it's a lot of copper and maybe some transformers and a bunch of control, right? And everybody forgets that, but that's why startups, when they say, hey, we have this lab scale thing and we're going to deploy it in our first integrated demonstration, their price points are never right because they always forget about the levelized cost of delivery because they don't have a good cost basis and design basis for how do we actually deploy the system at scale. So just, like a big plus one to what you were saying, Sean, is, a lot of this stuff just takes a lot of documentation and thought, and folks, don't have as much of experience of doing that on the data center sites at this scale, from what I'm aware of, at least.
Yeah, and just to add to that, my observation is, the generator industry, just in general, is a very mature industry, and they've been optimizing this technology for a certain application. It hasn't been for data centers, so we're sort of fitting a square peg in a round hole, which will fit if the sizes are right. Why do we tell kids square pegs don't fit in round holes? They can absolutely fit. The other issue is just the data center load is so unique. So, for example, data centers are never fully utilized, even though you need the infrastructure for 100% utilization. So your 100 megawatt data center is probably only pulling 60 megawatts, right? Well, generators, they're designed to have sort of an optimal point. The other issue is, especially with AI training workloads, is and the industry is still trying to figure out a good term for this. I've heard subsynchronous transients, and we'll just call it spiky workloads right now. Every single server is running the same exact workload, so the spikes are then transitioned out to. And if you're on a generator, that constant going up and going down puts a ton of stress on the unit. And these units are not designed for that, right? And so there's a lot of work to try to mitigate that. And that's one thing to keep in mind as well is, we're working with equipment that has not been designed for data centers and on-site generation. So don't take it as a given that you can just put in natural gas generation and you're good to go.
Yeah, well, and the I guess +2 now since I already +1. The transformers aren't really designed to take the transients either, and so in many cases the kind of attenuation strategy and the lifetime, right? So if you're all of a sudden putting these loads that the transformers were never really designed and don't have a good compensation strategy for, then your sort of premature death of transformers can be a pretty significant outcome as well.
Yeah, and by the way, that's different transformers, right?
yeah, different. Exactly, electrical transformer, not the TPU transformer. Well, awesome. Yeah, I mean, I think we have probably a few minutes left, and some questions are coming in here. Maybe it'd be worth sharing sort of. We kind of titled it War Stories, but maybe interesting things. We already sort of jumped in with some of the interesting work you guys did in Wyoming, but are there sort of other things that are maybe giving us an interesting directional indication of what could happen kind of in the future and how things could work?
Yeah. So if we're going to think about the future, there's one potential future where we're able to, not have this standby generator that's combusting hydrocarbons, and we could be using some sort of new technology, whether it be, emission-free hydrogen fuel cells or some new energy storage system. I mean, I think that would be ideal, as if there was a magic battery that you could store many days of energy. And, if there was an event, it could be recharged really, really, really quickly. And so, me and a lot of other people, we're tracking all these technologies. The challenge with new technology isn't that we're not sure if they're going to work or not. It's if they're going to be available in the timeline that we need them. So if you take an example like lithium ion, I think that took 7 decades to get where it's at right now. Well, we don't have seven decades, right? So what I'm interested in is what can we do as an industry, as a data center industry, to then partner with other industries to accelerate the commercialization and the scale up of these technologies so that we can take advantage of them.
Well, and the thing is, like, so that's where there's a lot of crosstalk between energy transition, kind of AI infrastructure. Ultimately, NASA gave us TRL, right? Like, what is the maturity of the technology? And it's not just, how long does it take, but how reliable and how much data do you need demonstrating that it's actually going to be primed to where you can run it as the main consideration on your plant, right? Traditional generation has decades, maybe a century of track record. People are pretty sure they know it's going to work, right? Then there's all kinds of supply chain and market readiness. And so it's actually really interesting because there are at least things we can think about, how mature does the supply chain need to be? How much performance do you need? And then ultimately, like, maybe how can you connect the dots on, can we run it in a demo scenario? Then can it be a good candidate for a backup or for sort of a parallel powertrain, although there may be sort of an additional cost, things like that. And then how do you kind of matriculate these things through, right? And then, like, it's fun to see folks like the Fervo Energy of the world, doing kind of deep well geothermal and thinking about, can we bring on new categories of renewable supply? And then again, how long do you have to run it before well, how reliable is that for how long, right? And so it's really, really interesting to sort of think about when folks bring that in from a possibility to sort of a first order actor in their designs. And, to your point at the very beginning of this episode, operating in a mission critical environment, the Navy actually has some really interesting standards for how they implement sort of new technologies and sort of keep chain of custody and inspection for things that are deemed to be critical in the operating system. So maybe even we can learn from some of that in saying, hey, this is a prime player in the powertrain versus this is kind of a thing that could help boost, right? It's a secondary consideration.
Well, the opportunity is with our industry is, as we go into the future, we can be building out with new, better, more efficient, clean technology. We spent a lot of time picking on power, but it's the same story with cooling as well. So there's a choice here, right? So we can continue to build out this infrastructure that our new economy is dependent on with traditional equipment, or we can be building it out with newer, better equipment, right? And I think that's a great opportunity for the data center industry to help scale this technology up and help reduce the cost and help bring credibility to it so that other industries can use it as well. So we talked about power. There's a lot of opportunities with cooling to try to do it without consuming, potable water. Even basic building materials like cement and concrete. There's an opportunity to build data centers with very low, embodied carbon building materials. So yeah, it's a really good time. We're at a point where we can do this smart.
No, amazing. We did have a question come in from Olaf asking about kind of efficiency potential, and we're sort of talking about this already. He highlighted specifically photonic chips and then immersion cooling, which the fun thing about the AI factory, if you will, is that at densities of 500 kW a rack, a lot of the traditional cooling methodologies just don't work because of the physics. You cannot air cool, 200 kW racks. It's just not doable. So you're gonna have to do something else. And so I've seen a lot of interesting, rear door exchangers and then direct to chip liquid cooling. I've seen a lot of immersion stuff on mining, but I haven't blockchain mining, but I haven't really seen that in the AI data center quite yet. But that's interesting. But yeah, what do you think about kind of some of these efficiency opportunities and how things will develop on kind of in that area?
Well, first of all, I need to do a back in the day moment. Sorry, but a lot of this stuff isn't new. 20 years ago, we were hacking hardware to improve the performance of our gaming PCs. And we were doing things like immersion cooling, right? We realized, oh, hey, I can take this whole rig and I can put it in mineral oil. and that'll and that's cheap, but it's messy. And so as I'm overclocking, my CPUs and stuff like that, it's all about trying to figure out how to pack more cooling. And so this cooling problem, a lot of us grew up with that from, like I said, hardware hacking, and it was so much fun figuring out different ways to just squeak more performance. We didn't have a lot of money. We're using these Celeron chips and whatever they might be, and we're trying to just get as much performance out of them as possible, which created cooling problems. And there was all kinds of, tons of fans and the mineral oil thing. So it was a lot of fun, but we were trying to eke out performance, right? And that's where the industry's is basically out there today. Is how do we eke out more performance? Where's the ideal temperature? And by the way, we're in an AI sort of era right now, but what's next? Maybe it's quantum computing, right? And we'll be having to sort of think about these things all over again.
Yeah, well, and just to double down on that, cooling is definitely being driven by the AI factory. But if you got to be near absolute zero, which traditionally has been sort of the environment in which quantum operates, that's a whole other game in and of itself. So that's a great point. We had another question come in here on kind of green hydrogen and fuel cells, and just kind of what role does that play as that develops. We kind of touched on it a little bit, but let's spend a minute talking about that.
I mean, fuel cells that's a cool technology. It's, it's been in spaceships, it's been in rockets and stuff for a long time. It's really cool. What we would like is a generator that didn't have any emissions, right? And so not only from like an environmental sustainability, but just to be able to sustain growth. All of the liabilities that come from burning fossil fuels on site, whether it be, getting permits in place or, community acceptance, things of that nature, fuel supply, all that sort of stuff. If our industry could get our hands on a reliable, emission-free, generator, and it be available at scale, like that would be ideal. This is a whole new era, handling, liquid hydrogen on a site and things of that nature. But these things are not insurmountable. It's all the science is behind us. It's all basically engineering and design and stuff like that. So that could be a future. Another future could be, nuclear or these advanced long duration energy storage systems that we're all looking at. Carbon capture, maybe that technology gets better. I'm tracking it all. We are tracking it all. And what we're probably going to see in the future is more of a bouquet of different solutions versus just one.
Yeah, I love it. I mean, I guess from my perspective, it's always when folks put the right metrics and the things that they're tracking on the table and sort of gain the perspective of, what do you need to win? And I think that just the statement of the enunciation of if we can get an energy producing asset and maybe extending that a little bit, that can take 70% spike in block load, plus be able to handle and mitigate transients so we don't have to do it, like a couple other details. And then say with a price point and a carbon intensity that are X and Y, right? We can have a very different conversation about how do you align stakeholders and think about delivering that. Yeah, we got just like a minute left. I think that's actually a really good stopping point. I think when Barak and I started this conversation, a lot of it was bringing folks that have deep, boots on the ground experience working at, one of the 4 C's. So knowing where their home is, and then also being kind of curious about where is the most interesting other C. And so I think we had a really good conversation here that allowed us to, pick your brain for a little bit, but also kind of compare and contrast notes. So I really appreciate the time and you joining us for the session here, Sean.
Yeah, sounds good. Thanks, everybody.
Thanks, Sean. It was amazing education, at least for me, because I'm not from that area. So I appreciate that.
Absolutely. Amazing.